part B. In the conversion of 3 to 4, sodium amide functions as a base and ammonia is a solvent. Okay. Draw a mechanism for the conversion of 3 to 4 and make sure to show the transition state for this process. Okay, so I drew the NH2 with a minus on there just to show that it's gonna act as a base, and the ammonia is our solvent. So coming back to our structure here, we have NH2. Now just remember that the sodium is a counter ion that just stabilizes a nucleophile, and in this particular SN2 process, the sodium is not gonna be important. So I have minus charge on that nitrogen that's gonna grab or abstract that hydrogen on our substrate compound 3, and it's gonna place the electrons on the nitrogen for our second arrow. And it's gonna make the nucleophilic center. Why did I do that? Well, that's because we need to form a ring around the nitrogen, and when you compare the compound 3 and compound 4, the difference between them is the ring around the nitrogen. So in compound 3 I don't see that, in compound 4 I see that triangle. Other than that, the leaving group of the bromide is clearly the answer, because in compound 4 I don't see bromide. Okay, so our nitrogen is gonna undergo intramolecular nucleophilic attack to form another bond within itself, within the substrate itself. So for now, it's gonna look like this. Okay, nitrogen has two pair of lone electrons, so meaning we have 4 lone electrons. Well, they go in pair, and we have minus charge that's going to attack our alpha carbon that bears the halide, and then it's going to undergo through the back attack. Okay, just like we saw in inversion process, inversion of stereochemistry. And we show, you should be aware that there's a stability with the back attack because of the molecular orbital theory. And yes, well, I cannot go too far in these problem solving videos, but anyway, it's gonna undergo through the back attack nucleophilic attack, and then it's gonna have the leaving group, or the bromine is a leaving group here. And now notice that you can form a triangle here. This is a single bond, so they can be rotationally, they can rotate, they can undergo through the conformational change with a single bond. And seriously, you're gonna get the triangle if you just rotate. Okay, I'll show that. So you're gonna have like a bond that used to be this, now you have 180 degrees rotation. And that only works with a single bond though. And once you are in this form, and say this nitrogen is gonna form a bond with our alpha carbon here, and then that's gonna be our this new bond in compound 4. Okay, new bond. Alright, so that should be it for part B for the mechanism, but we still have to draw the transition state that's between this and compound 4. So, well, I will actually draw it better so that it's more visually understandable. Oh no, that's bad. Okay, for now I kinda distorted the very bottom double bond, but it's not a major issue. So I forgot minus charge on the nitrogen, and which is gonna attack our alpha carbon on the backside, and we're gonna have a bromine, right? So I mean, this is essentially the same thing on the left and right. And you're gonna form that green bond that I just showed in the compound 4. Oh, transition state, what am I doing? Okay. Now remember that we have a minus charge on the nitrogen that's spread over nitrogen and the carbon, the bromine, the leaving group. Therefore, I'm going to have a delta that shows a partial negative charge spread over. And when you identify the transition state, you must have a bracket around it, and then the telephone pole sign. Alright, that's it for part B. Now let's move on to part C.